Let's take a look at problems from section 1.3. And the first one we want to look at is an absolute value equation. Now, one of the things we want to talk about is, before we start the problem, is the fact that if I have some algebraic expression, let's call it x, and I take the absolute value of that and set that equal to some positive value c, then this is really a compound equation. And either x equals c or x equals negative c. And I can't actually begin solving or working on this absolute value equation until I rewrite it in its expanded form, which does not include absolute values. So notice the form of this is that the absolute value is isolated on one side of the equation and a positive constant is on the other side. So I notice that the equation I have is not yet in that form. So to get it in that form, I'm going to subtract 20 from both sides of the equation. So I now get the absolute value of 2y minus 5 is equal to 15. So now I do have the form talked about in this property of absolute value equations. I have a positive number on the right side of the equation, or it could be on either side, but on one side of the equation, and I have an isolated absolute value bar applied to an algebraic expression on the other side of the equation. So I'm going to apply this rule to this equation. I'm going to rewrite it in an equivalent form that does not have absolute value bars. So 2y minus 5 is either negative 15 or 2y minus 5 is positive 15 if the absolute value of 2y minus 5 is 15. And so I solve the equation on the left. 2y has to be negative 10. If I divide both sides of this equation by 2, then I find out that y has to be a negative 5. The equation on the right also needs to be solved. I also begin this one by adding 5 to both sides of the equation. And now I obtain that 2y has to be 20. If I divide both sides by 2, I determine that y, in this case, has to be 10. So when y equals negative 5, what's inside of these absolute value bars, 2y minus 5, becomes negative 5. I'm sorry, becomes negative 15. Sorry. And when y is 10, what's inside of these absolute value bars becomes positive 15. And so that's how the two solutions result. So typically in my math lab on a problem like this, you're going to be entering a solution set. And in this case, the solution set contains the numbers -5 and 10. In our next problem, we have an inequality whose solution set we want to write in set builder notation as an interval and as a graph. And this is an absolute value inequality. Now the rule that we're going to be using here about absolute value inequalities tells us if the absolute value of x is bigger than c, and again, x is an algebraic expression, c is some positive constant, that's why we're using the letter c, then either x is less than -c or x is bigger than c. And so remember what this means is that whatever my algebraic expression is, I need the absolute value of that expression to be more than c units from 0. Because remember, that's what absolute value actually means. It's the measure of how far my value number is from 0 on the number line. So in order to be more than c units from 0, you have to be to the left of -c or to the right of +c. Now this greater than symbol could be replaced with a greater than or equal to, as we see is the case in our inequality that we're solving. So I'm going to rewrite this so I have the absolute value expression isolated on the left side of the inequality, and I'm going to rewrite this as the equivalent compound inequality. So x plus 3 has to be less than or equal to a -18, or x plus 3 is greater than or equal to a +18 if the absolute value of x plus 3 is going to be bigger than or equal to 18. So in other words, whatever x plus 3 is, its value is a number that's more than or exactly 18 units from 0. So this is pretty straightforward. I'm going to subtract 3 from both sides of both inequalities. And once I do that, both inequalities are actually in simplified form. So x is less than or equal to -21, or x is bigger than or equal to 15. So it's very important that the connecting word here is or. That has a precise mathematical meaning, and it basically means this statement is true, this compound statement is true, if either x is equal to -21 or left of -21, which means it's smaller than -21, or if x is bigger than 15 or equal to 15. So if I want to write that in set builder notation, that is the set of all x such that x is less than or equal to -21, or x is bigger than or equal to 15. As an interval, I can move indefinitely to the left of -21, including 21, and I unite that interval with 15 and all the numbers to the right of 15. So remember, a negative infinity means indefinite movement to the left. Gives me a very precise and brief way to say that. And a positive infinity means indefinite movement to the right. A negative infinity symbol is always to the left of an interval, always enclosed with a parenthesis. Positive infinity is always to the right of an interval, and again, always enclosed with a parenthesis. These are always enclosed with a parenthesis because you can't equal infinity. Infinity is not a number, it's a description of a pattern of behavior. And then finally, I want to give this as a graph. So I start off by writing a number line, and a bracket or a closed circle can be above negative 21. And I shade to the right. And I show an arrow indicating that I can move indefinitely to the right. And I must also show a positive 15. And again, that I am shading to the right of 15. And an arrow to show that I can move indefinitely to the right. So that's my graph. Those are the three ways that we describe the solution set, or can describe the solution set, as a set using set builder notation, as an interval, in this case this interval is a union of two intervals, or as a graph. Here's an example of an application that relates to an absolute value inequality. We want to solve this absolute value inequality where the absolute value of 98.0 is less than or equal to 0.2. If x represents the values of basal body temperature, this inequality represents a range of measurements which are the target value of basal body temperature if the thyroid gland is functioning properly. Find the set of ideal basal body temperature values. Graph your solution set on a number line. All right, so again, we need to learn how do you rewrite an absolute value expression less than or equal to a positive constant. So first let's talk about and unfold this. If I have the absolute value of some algebraic expression and it is less than a positive constant c, then x is got to be greater than a negative c and at the same time less than a positive c. Here the connecting word is and. And so another way to write this is that x has to lie between negative c and c. And notice essentially what we're saying is we want whatever the value of this x is, we want it to be a number that's less than C units from 0. So that would essentially mean that that value has to lie between negative C and C. So we're going to apply that to this absolute value inequality. So this means, so remember, these are two, you can express this by actually writing the word and two simple inequalities connected with the word and, or you can use this more concise way of writing this, that x is bigger than negative C and less than positive C. So these two expressions, inequalities, these two inequalities say the same thing. This absolute value inequality says the same thing. This compound inequality says the same thing as this compound inequality. All right, so in our case, our C is 0.2. So my algebraic expression, x minus 9.8, has to be x minus 98.0 has to be bigger than or equal to a negative 0.2 and at the same time smaller than or equal to a positive 0.2. Another way to look at that is this has to lie between negative 0.2 and positive 0.2 and include negative 0.2 and positive 0.2. All right, so we've rewritten our absolute value inequality without an absolute value. So these two inequalities say the same thing. So to solve this, I just need to add 98.0 to all three segments of the inequality. It's really two inequalities combined and written in a concise form. The word and is not visible here, but it is implied. So I get 97.6. When I add negative 0.2 to 98, 0.8, 97.8 less than or equal to x less than or equal to 98.2. So what this really means in light of what the problem is discussing is that ideal basal body temperatures lie inclusively, meaning we're including the 97.8 and the 98.2, between (97.8) and 98.2. That's one way you could say that. And it's actually degrees Fahrenheit. We know that wasn't stated in the problem, but this is a body temperature measure that's measured in degrees Fahrenheit. All right, so here the absolute value basically says, what this is really saying is, if I look back at the original inequality, it's really saying that my body temperature needs to lie within 2/10 of a degree from 98 degrees. And so that's essentially what it's saying if I take my basal body temperature. And so I'm able to write that as an absolute value inequality. All right, here we have two special situations. You'll notice in both of the previous statements about how to rewrite an absolute value inequality without an absolute value involved, the number on the right side of the inequality was always positive. Here we have two negative numbers. So when you see the absolute value isolated on one side of the inequality and a negative number on the other side of the inequality, there's actually no calculations for you to do to solve this. But you need to understand that absolute value always results in either 0 or a positive number. So, if I look at my number line, here's 0. The positive numbers are to the right of 0 on the number line. And both 0 and the positive numbers are to the right of every negative number, which means 0 and any number that's positive is always bigger than absolute value. So this statement, absolute value of x plus 3 greater than or equal to negative 18, will always be true. So we're really saying something that's always positive or 0 is always bigger than something negative. It's never equal to something negative, but as long as we can make the greater than part of this true, it will always be true. So the solution set, so it doesn't matter what value I give to x, the solution set is the set of all real numbers. So it's the set of all x such that x is a real number. And so we were asked to write the solution set and explain. So that's what we've done there. Now here we see we want to find the solution set for absolute value 2x minus 5 less than negative 27, and we want to explain that. Well, something that's 0 or positive is never going to be smaller than something negative. So absolute value of 2x minus 5 is always 0 or positive. And therefore never smaller than a negative number. Another way to think about what we're saying is there's never an x value that will ever make this true. So the absolute value of 2x minus 5 less than negative 27 will always be false. So that means that the solution set is the empty set. Okay, so the solution set is empty. There are no solutions for us to put in it.